Okay, so you're going to need your own exam paper for this. There's one I had no idea about, and I've marked the most difficult questions according to the IB, the one that the least people got right, and the most discriminating, the ones only the smarty pants got right. Alrighty, how many moles? So I'm going to put a mole here. 32 grams of sulfur dioxide. So moles is going to be mass over molar mass, which is 32 given in the question. And the molar mass of sulfur and oxygen are also given in the question. 32, 16, 16, 32 over 64, so that's going to be a half. Then you just got to use simple molar ratios. 8 is to a half, as 4 is to, well, that's my unknown x. So 4 over x is 8 over a half. So my unknown is a quarter. Hey, nice. Next one's the most difficult question. The trick seems to be some sort of Kelvin something, converting to and fro. All right, so what I use is a PV over T at the beginning is PV over T at the end. Now, you notice that R's missing, or R's a constant, don't worry about that. And N seems to be missing from this, the traditional PV equals nRT. Well, the number of moles don't change if the gas is not adding or removing molecules or atoms. So since they're both the same, I can use this PVT. So the pressure at the beginning, well, it's the same pressure, and it makes it even easier. Alrighty, so I'm going to take away the two pressures. So the first volume is 10, and the second volume is 9. The first temperature is 300. Don't forget, you're adding 273 for the Kelvin. And my final temperature is X. Okay, so I've got 10x equals 9 times 300. So that's x equals 9 times 30, which is 270. This is Kelvin. All the answers are in degrees C. Oh, so that's going to be minus 3 degrees C. So that's 2A. Oh, that's the hardest one you got? Okay, 2A. Got to convert to and fro with the Kelvin. Number 3 was the second easiest question. A little bit of stoichiometry. So concentration. So concentration is going to be moles over volume. So I can see the trick with the volume. You've got to convert to decimeters cubed. So to divide that by 1,000 to get decimeters cubed. Have they given me the moles? No, they're giving me the molar. They give me the mass, so I can handle that. Moles is mass over molar mass. So that's 0.5 multiplied 0.5 divided by 84. Well, there we go. So what one's that? 3B. What they've done is they've moved the 84 down to the bottom to get 84 at the bottom. And then they've done the 250 divided by 1,000, like that, and kept the 0.5 at the top. So that's B. Question 4, emission spectrum. Lines converge at high frequencies. Yeah, you just have to know that. Electrons and transitions to n equals 2 are responsible for lines in the visible region. I'm not so sure about that one. It's only if the electron goes down to n equals 2 do you get visible, not if it goes up to n equals 2. So that's ambiguous. And 3, lines are produced when electrons move from lower to higher energy levels. When an electron goes from a lower to a higher energy level, no, that doesn't release a photon, which would make a line. So that 1's definitely true, 2 is ambiguous, and 3's wrong. Oh, that's good. So it's 1 and 2, so 4 is A. Question 5. First ionization. There's a couple of tricks they can play on this. How easy it is to pull off sequential electrons from an atom. So looking at element X, the first one's easy and the next two are difficult. So if one electron comes off easily and the rest are more difficult, then that must be one electron in the valence shell. So X has to be group 1. So X has to be lithium. So lithium's group 1. Is that enough? No. And for Z, it can't be beryllium, because beryllium, there's 2 electrons that come off easy, because beryllium has electron arrangement of 2-2. So it can't be beryllium. So if it's lithium and not beryllium, is that enough? Yes. So that's B. Lithium and not beryllium is B. Question 6. Which oxides produce an acidic solution when added to water? So if you've got the periodic table, I remember here that sulfur's here, and sulfur dioxide, that's one of the main gases responsible for acid rain. So the non-metal oxides produce acids. Does that help? Okay, so Al2O3, that's amphoteric, so that can produce both an acid and a base. But we can ignore the first one, because SiO2, that's sand. That doesn't dissolve in water. That's why they're beaches. So I is wrong. The next one is 2 phosphorus oxides, and the next one is nitrogen. Yeah, so 2 and 3 are correct. 2 and 3 are correct because they're non-metal oxides. So what does that mean? That means the answer is C, 6C. Question 7. So which one's the easiest to remove an electron from? Well, it can't be C or D, because they have a much higher charges than A and B. So it's harder to pull an electron off of a +3 and a +2 than it is to pull one electron off of a +1. So is it easier to pull an electron off of sodium, or is it easier to pull an electron off of magnesium? So sodium is 2,8, magnesium is 2,8,1. So which is going to be easier? It's going to be easier to pull that one off, isn't it? Because the electron's further away from the pull of the nucleus. So 7's going to be B. 8. So the square brackets is the complex. I know that SO4 is 2-, and I know that Cl is minus. I know that water is neutral. So now I just have to work out what that is there. Isn't that going to be +3? Because it's all got to equal 0, because overall there's no charge. So iron's +3, and what's the charge of the complex ion? This has to be 2+, if this is 2-. So the answer is D. 8 is D. SO3 2-, the sulfite ion. All right, let's draw the Lewis structure. Sulfur is in group 16, 6 valence electrons, as is oxygen, and a cheeky 2 extra electrons from the charge. Divide that by 2 because I want electron pairs. VSEPR theory, electron pairs. 6 and 6 is 24, so it's 13. Sulfur goes in the middle because it's the first one. And I'm going to put oxygen around the outside evenly. 10 more lines to go. 1, 2, 3, 4, 5, 6, 7, 8, 9. 10. So I've got 3 bonded pairs and 1 lone pair around the central atom. So that's going to be a trigonal based pyramid. So that's C, 9C. It's the same as PF3. Next up, 10. That's a strange one. I'm always in admiration of how they managed to find weird ones that I've never thought of or seen before. So using the same methodology, I've got 7, because it's in group 17, 7 valence electrons, plus 7 plus 7 minus 1. Got a positive charge, so I've lost an electron. So that's 14, that's 10. Okay. Chlorine goes in the middle and fluorine on the outside. And I've got how many more to put on? I've got another 8. 1, 2, 3, 4, 5, 6, 7, 8. So how many lone pairs on the central chlorine? There's 2 lone pairs on the central chlorine. 1, 2. And how many bonding pairs? There's 2. So it's 2 and 2, which gives the answer D, 10D. 11, which has the highest boiling point. It's organic chemicals, so I bet it's the one with hydrogen bonding. I'm just looking at that. I can see that's 11D. Yes, but let's go through them. The first one is ethanol. They're trying to trick you. If it's CHO, it's an aldehyde. But if it's C with an O and an H, it's an alcohol. And the alcohol is the only one with the potential for hydrogen bonding there. So no hydrogen bonding there. Hydrogen bonding is the strongest intermolecular force. Then you've got fluoroethane. That has a strong dipole going that way, but dipole is a weaker intermolecular force than the hydrogen bonding that we're looking for. Methoxymethane. That molecule has a dipole as well. It's bent. And the final one has hydrogen bonding, or the potential for hydrogen bonding there, because there's a hydrogen attached to either a fluorine, an oxygen, or a nitrogen. And so of all the molecules, it's only D where the hydrogen is attached to either F, O, or N. And just for completeness sake, that isn't a hydrogen bond, nor is that. That's an intramolecular bond. Hydrogen bonds are intermolecular between the molecules. Question 12. Hell's bells. Some sort of supercyanide death molecule. Okay, so I've got a carbon-carbon double bond in the middle. And then I've got a couple of cyanides coming off. Okay, a couple of cyanides coming off here. Oh, and a couple of cyanides coming off there. So I suppose you've got to know that a cyanide contains a triple bond. Put in the lone pairs just for completeness. So how many sigma and how many pi in the total molecule? So every bond has 1 sigma bond. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 sigma bonds. A single bond is a sigma. A double bond is a sigma and a pi. And a triple bond is 2 pi's and a sigma. So how many pi's do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 and 9. So 12 is A. Moving on. 13. Hybridization. There are some exceptions to this. There's some questions they could ask that wouldn't fit the IB rules. Hopefully they've avoided that. All right. So if I've got this here on the O, I've got a CH3 there. I've got an N. Right. So the carbon, well, that's sp3. It's a bond angle of 109 degrees. It's going to be sp3 for the carbon. Is that enough? No. This has a bond angle of 120 degrees. And that double bond there, that implies to me that's going to be sp2. Is that enough? Oxygen's sp2, carbon's, yep, 13D. 13D. 14, a bit of Hess's law. These normally look trickier than they actually are. This one looks quite straightforward to me. Okay, so I've got 3 carbon monoxides. I've got 1 there and 1 there. So it looks like if I flip this equation, I've got it on the right side now, goes over to there. And if I double it, I've got 3 carbon monoxides in total. I bet that's it. Yeah, it all just falls into place. So if I flip it, I'm going to have to change this sign from a plus to minus. And since I doubled it, I'm going to have to double the number. And then I'm just going to sum it. Minus 3 plus minus 11 times 2, which is going to be, which is A. 15. Oh, this is an unusual reaction. 2 solids and it gets cold when you mix them. Unusual to have 2 solids reacting. And endothermic's also unusual. Alrighty, so if delta H theta is positive, it's going to be endo. And the temperature is going to go down. And if it's endo, the graph looks like that. So the products are going to have a higher energy or enthalpy than the reactants. And anything with higher energy is less stable. So in this case, the products are less stable than the reactants. So it's going to be 15C. 16. 16, oh, I loathe these questions. I can't think of an easy, quick way to remember it. Okay. So I've got 1 gas and there's no gases there. So disorder is decreasing. You've got to look for the gases. Disorder is decreasing. So the change in enthalpy is negative. For S, you can just say disorder. It makes the same thing. So that gives me A or C. Well, okay, so it's A or C. Now I could just make a broad guess and say delta H. I've got 2 things and I'm making 1 thing. So I'm bond making, and bond making is exothermic. Bond making is exothermic, turning 2 into 1. Is that the answer? Minus, minus? It is. It's, oh. There's another way to do it, where you can just push it through delta G is delta H minus T delta S and do some, see what happens to delta G when you change T, but I like my shortcut way of doing it. So 16 is C. Question 17. I don't know why these cause so much trouble, this one. So exo, that's going to be, the temperature is going to go up for the surroundings. So that's going to be bond making. So of A, B, C, and D, one of them is going to be making stuff, and 3 of them are going to be breaking. You just have to work out which one's making. Okay, for A, you're breaking a bond there, so it's not that one. For B, you're pulling off an electron, you're breaking something, it's not that one. C, I've got potassium chloride and I'm snapping it in 2, so that's breaking, it's not that one, so it has to be D. Yeah, I'm making stuff. I've got a chlorine atom and an electron, make a chloride ion, I'm making stuff. Bond, bit of a loose term, it still works for this one. So 17 is going to be D. So I've got excess hydrochloric acid. I've got as much of that as I need. And then I've got 1 gram of that chemical in both situations. Now the only difference here is that I've got a concentrated hydrochloric acid and dilute hydrochloric acid. So that means the reaction is still going to finish and make exactly the same amount of product, because that's in excess. I'm not going to run out of that. And the limiting reactant's the same each time. But it's going to be slower. The dilute one's going to be slower. Is that enough to get you through? What's the same for the reactions? The initial rate isn't the same. Nope. The dilute one's going to go slower. B, the total mass of carbon dioxide produced. That's true. It might take a little longer with the dilute one, but that one's true. C, the total reaction time. No, the dilute one's going to take longer. And D, the average rate of production. No, the dilute one's going to have a lower average rate. So that's going to be 18B. 19 was the easiest question. It was 92%, I think, of people got this right. What decreases the activation energy? So we've got this diagram here. That's H, that's progress of reaction. And you've got activation energy. So what's going to bring that down? Hopefully you remember that's going to be the catalyst. So that's going to be 19B. The time is proportional to 1 over the rate. So looking at experiments 1 and 2, Y is unchanged, and I've halved the concentration of X. I've halved the concentration of X, and it took twice as long. So that is an order of reaction 1. You halve the concentration, it takes twice as long, that's a 1 order of reaction. And so for Y, let's compare experiments 1 and 3. X stays the same, and Y is halved. As I halve Y, it takes 4 times as long. So you halve the concentration, takes 4 times as long. That sounds like an order of reaction 2. So that's 1 and 2, which is 20A. Yeah. 21. 21, which is not consistent. Oi, 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 oi. Now, I think there's a very evil distractor here. I think B is a very evil distractor because it's termolecular. There's 3 hitting at the same time, extremely unlikely to happen. But anyway, so the answer is C, and I'll just kind of back explain why that is. So you have to look for the slow part because that has the highest activation energy and is also the rate determining step. And if I look at C, I've got NO plus O2 goes to NO2 plus O. Now, the trick is to work out the rate equation. You put rate equals K, and then you take the contents of this slowest step, or the rate determining step. So in this case, I've got an NO, and I've got an O2. And that doesn't match the given rate equation. So it must be C. The others do match. 22, so as the temperature increases, the value for Kc also increases. So as the temperature increases, since Kc is products over reactants, as Kc increases, the amount of products must go up and the amount of reactants must go down, which means as temperature increases, the forward reaction is going to be favoured. Oh, so that's 22A. That's not too bad. 22A. You just have to know this. I forgot to teach this last year, but the kids read the books anyway. Can't expect to do everything. So for the reaction that's equilibrium, you want the entropy value to be at the maximum, the most kind of disordered, and you want the Gibbs free energy value to be at a minimum. Maximum, minimum is 23B. You just have to learn it. 24, what are acting as Bronsted-Lowry acids. So if you remember, a Bronsted-Lowry acid donates a proton. So there's going to be one on each side. What donates a proton here? I missed out that negative. Yeah, it looks like that this donates a proton. It had H2 and then it went to H1, so that's lost a proton. So that's one species. And on the other side, what's lost? The water seems to have lost an H+. It went from H2O to OH-. So it's H2PO4- and H2O, which is D, 24D. 25, increasing pH, okay. So underneath each one, I'm going to write if it was made from a strong or weak acid, strong or weak base. So sodium chloride's made from sodium hydroxide, that's a strong base, and hydrochloric acid, that's a strong acid. If it's a strong and a strong, that's going to give me pH of 7. Ammonium chloride, well, it's made from ammonia, that's a weak base, and hydrochloric acid, that's a strong acid. So it tends to track with the strong. Whatever was used to make it, it tends to track with the strong. So pay attention to which is the stronger one. That's the way the pH is going to go for the salt. So a strong acid is going to be pH of less than 7. So it's going to be less than 7. Sodium carbonate made from sodium hydroxide, which is a strong base. And carbonate, well, that's carbonic acid. That's a weak acid. Again, it tracks with the strong base. It's got a high pH, so it's going to be more than 7. And the final one, sodium ethanoate. The ethanoate comes from ethanoic acid. That's a weak acid. And the sodium from sodium hydroxide. That's a strong base. It tracks with the strong base. And so that's also going to be more than 7. Interesting. I thought there'd be one for each combination there. So increasing pH. So it's going to be NH4Cl, and then it's going to be NaCl. I hope that's enough because I'm unsure which is the position of those two. Yeah, that is enough. Good. Okay, so that's 25C. 26. So a Lewis base can donate a lone pair of electrons. So we just have to check which has no lone pair. I've got OH-. Yeah, that's got 3 lone pairs. I've got the ammonium ion. Yeah, there's no lone pairs on the ammonium ion. So that's the answer. This one here, B. Just for completeness sake, there's water. It's got 2 lone pairs. That's got a lone pair as well. So the answer must be 26B. 27. Oh, okay. pKa of 5.1. Now that means that it changes colour at pH 5.1, if that's the pKa 5.1. I don't like the way they've got colour A and also there's ABCD, and colour B and there's ABCD for the possible answers, and IN is indium, and I think it's all just a bit of a mess. But anyway, let's carry on. So if I add H+, I'm going to shift the equilibrium over to the left, and there'll be more of colour A. So if I add H+, I'm going to get more of colour A. Is that enough? No. If I add H+, I'm also going to get more HIN, but it doesn't mean necessarily that I'll have more HIN than I have iron minus. It just means that my amount of HIN's gone up and my amount of iron minus has gone down. Next one. Well, if I add some OH minus, it will react with the H plus and shift the equilibrium to the right. And I'll have more of colour B. So if I add OH minus, I'm going to get more colour B. Is that an answer? Yeah, that's A. Now don't forget it changes colour at 5.1. So if I can add OH minus to get it over 5.1, then I'm going to get colour B. So 27's A. All right then, the second most difficult question and the most discriminating question. If you can get this right, only the smarty pants can get this right. I wasn't really sure why this one was so tricky. I found others a lot more tricky. So it just wants to know the oxidizing agent and reducing agent. So you have to know the oxidation state rules. All elements are 0. Hydrogen's +1 in a compound. Oxygen's -2 in a compound. And it has to add up to the charge on the ion. Hydrogen's +1 in a compound, which means phosphorus is -3 here, because it's got to equal 0. And then hydrogen's +1, oxygen's -2, it's got to equal -1, which means this has to be +3. Is that right? No. Is that +1? So this is what's called disproportionation. There's a little trick here. The phosphorus does both things. It goes to the pH 3 and it goes to that one there. The number goes up and the number goes down. So in this case, this is reduction because the oxidation state went down. If that's reduction, this must be the oxidizing agent. The oxidizing agent is itself reduced. And this must be oxidation because the oxidation state went up. It went from 0 to +1, which means this must also be the reducing agent. So it's P4 twice, which is D. 29, what describes the flow of electrons in a voltaic cell? Oh, how tedious. Alrighty, so just to refresh your memory, the voltaic cell, let's just do the one that I can do quickly from the top of my head. I've got some zinc here, and I've got zinc 2+ in there. And then I've got some copper here, and copper 2+ there. I know that the zinc is the most reactive. It's got to end up as an ion. So the zinc ends up as an ion. And then flip it all backwards. All right, that's what I remember about that. And it won't work unless you pop in that salt bridge. All right then, so what describes the flow of electrons in a voltaic cell? Well, I know that they go from the negative electrode, and this is the negative electrode here because it's giving off electrons. This zinc is making zinc 2+, and when it makes that zinc 2+, it's giving away 2 electrons. Now you need a lot of pre-knowledge to kind of get this one up and running. I think that's true. So the electrons go from the zinc around the external circuit. This is also the negative electrode. So from the negative electrode to the positive electrode. So it's B. 29 is B. Oof. A lot of heavy lifting for that one. 30. Oh. It took me ages to make this video because it turned out a lot of the textbooks were wrong. 30. Hell's bells. Delta G theta equals minus NFE there. And it equals minus RT ln. And that K, annoyingly, is Kc, is the equilibrium constant. Oh, that's RT. All right then, if the standard electrode potential is negative, so if you've got a battery with a negative voltage, then that battery doesn't work. It's garbage. So if your voltage is negative, it doesn't work, which means delta G must be positive, which is non-spontaneous. Is that enough to get me through? Oh no, it just gets me to C and D. So delta G is positive because your battery doesn't work. Now the equilibrium constant, that's going to be products over reactants. If I want a battery that doesn't work, do I want more products and I want more reactants, don't I? So I want this to be a big number, and I want that to be a small number. So overall, that's going to be a small number. So I think I want Kc to be small. So C, 30C, yeah. So I want Kc to be small because I don't want my battery to work. Oh, now sometimes they play nasty tricks on you here. They haven't really. This one looks a lot worse than it actually is. They put these in the correct order, like they are in the data booklet, the most negative to the top. And they've also put the electrons on the left-hand side as reduction, which is just how they are in the data booklet. So they're not messing you like they could mess you about. So if you want to know the voltage, you just find the difference and make it positive. So find the difference and make it positive. So the difference between this and this is 1.59. If the battery works, which it says it does work, or it doesn't claim it doesn't work, yeah, what's the cell potential? So it's going to be positive. Now, don't be tempted to make it negative. That's for batteries that don't work. And you see there's a whole bunch of 2s and 3s in the equation. And so people think, oh, you've got to multiply by 2, you've got to multiply by 3. No. It's as simple as find the difference, make it positive. So 31 is D. (32) acidified potassium manganate. That's an oxidizing agent. So they want to know which of these can be oxidized. Well, primary alcohols can be oxidized, secondary alcohols can be oxidized, and tertiary alcohols cannot be oxidized. So we basically got to spot which one's the tertiary. So this one here, it's OH, that's primary. 2 looks a bit complicated, I'll come back to that. This one here, I'm just putting zigzags. There might not be the right amount of zigzags. That's a secondary. So is that enough? Definitely I and definitely I. Is that enough? No, we do have to decide about 2. Okay, so 2, I've got a carbon with a CH3 with a CH3. And another CH3. A carbon. 2 hydrogens here. And then an OH. Oh, that's primary as well. So it's 1, 2, and 3. Now, how can you tell if it's primary, secondary, or tertiary? Find the OH, find the carbon attached to it, which in this case is this one here. How many carbons directly attached to it? Just 1. It's primary. Find the OH, find the carbon it's attached to. How many carbons are directly attached to that? 2. It's secondary. Find the OH, find the carbon it's attached to. How many carbons directly attached to that? Just 1. So that's primary. So it's all of them. So that's going to be 32D. (33), this unhealthy obsession with benzene. I've never seen benzene. Doing chemistry for 42 years. You can't really add stuff to benzene. You can't really break this ring. It's pretty strong in IB. You can substitute, you can switch stuff out, you can switch X for Y, but you can't really add stuff. Is that enough to get me through? It undergoes addition reactions? No. It contains alternate single and double bonds. Well, it depends which model you use, doesn't it, really? So it could be that one. I'm not convinced that one's right or wrong yet. You could use that model. So B, maybe. H1 NMR shows 6 signals. No, that's not true. There's only one hydrogen environment for benzene, and they all occupy the same hydrogen environment. So C's wrong. And D, H1 NMR shows one signal. That's good. And it forms a single isomer. So there's only one way you can put bromine on here. Well, if we go back to this original model, the more advanced model with the ring, is it true you can only put bromine in one position? Yeah. So I think the answer is D. And so the IB is assuming that this model is not the one you're using, that you're using this model with the delocalized electrons. Fair enough, it's more accurate. 34, oh, some sort of big old ester. If you ever see two oxygens, it's a carboxylic acid or an ester. And since they're in the middle, it looks like an ester. So let me draw it out. I've got 1, 2, 3, 4. Then I've got a carbon, one there, and one there. Okay, I've missed out the hydrogens. So to make an ester, you need an alcohol, carboxylic acid, and a strong acid, specifically sulfuric acid, as the catalyst. Ooh, that's a bit wrong. Got rid of that. Okay, so I think about it as you cut it here, cut with two oxygens on one side between the carbon and the oxygen. So that unambiguously gives you this cut. Both oxygens on one side between the carbon and oxygen. This is the acid. So it looks like it's made from butanoic acid. Is that enough if the acid's butanoic? Nope. And then this is the alcohol here. So the alcohol is this, this, this. And then I've got the O and the H there. So that's a propan-2-ol. So the answer is D. 34D. So when I put the cut here, I put the water back in. So there's an H from the water, and there's an OH from the water. So when you react an acid with an alcohol, the water comes off. And when you try and work out what the hell happened, I put the water back on again. 35 is the most discriminating. A guy called Tent in Thailand told me his quick way of remembering it, which is 1, 2, 3, bang. SN1 is 2 steps for tertiary haloalkanes. And it's fast. So hopefully that will get me through. So A, 1 bromopentane follows SN1. 1 bromopentane is a primary haloalkane. Nope, only tertiary haloalkanes follow SN1. 2 bromo 2 methyl butane. So 2 bromo 2 methyl butane. That's a tertiary haloalkane. So that follows SN1. No, they say SN2. That's wrong. C, 1 bromopentane is a slower rate than 1 chloropentane. So it's the strength of this bond that here. The weaker this bond, the faster the reaction. And so this is weaker, and this is stronger. So this one should go faster. No, they said it goes slower. So C is wrong. The way I remember the pattern of the bond strengths is, well, I know that CF is a really, really strong bond. That's used in Teflon, which is like the coating of saucepans. Extremely resistant to heat, and you heat it up, that bond is one of the strongest you can form. So that's how I remember the pattern. So it must be D, 35D. (35D), reaction with 1 bromopentane occurs at a slower rate than 2 bromo 2 methyl pentane. So this one here, they're claiming, is the fast one. Yep, it is fast. It's a tertiary haloalkane, and bang is fast. I just remember that hydrogen likes to go with its brothers, So whenever you do this reaction, just try and stick the hydrogen with the other ones. So I've got but-1-ene. I better put in the hydrogens since I need to know where they're going to be, so I can add the hydrogen with its brothers. And I'm adding HBr. So I've got HBr. So the hydrogen bromide has to go across the double bond, and so this is going to go here to be with his brothers because there's two of them. It wouldn't go over here, there's just one of them. And so this bond breaks and the bromine goes there. So that's 2-bromobutane. 2-bromobutane, that's B. 36 is B. 37. I got this one wrong. I miscounted. Hell's bells. So a chiral carbon has one with 4 different groups attached to it. I've got C, C, C. Oh, so not that one then. And not that one. And not that one before we've even started. Then there's a hydrogen there. Then I've got a C and an H. There's a Cl, a C and a Br, and an H and a CH3. Okay. This one's chiral because it has 4 different groups. You have the hydrogen, the chlorine, this funky triple carbon thing here, and this double carbon there. And for the same reason, that one's also chiral. So there's 2 chiral carbons. Tend to be marked by a star. This one's not chiral. Look, hasn't got 4 different groups attached. So that's 2. 37 is C. 38. Two-methylbutane. So H1NMR counts the amount of hydrogen environments and the ratio of the hydrogens in each environment. So what's the ratio of the areas? So I need to find out how many different hydrogen environments there are. This is the same as this, is the same as this, is the same as this, is the same as that, and that. These are the same. So that's 1 hydrogen environment with an area of 6. This is unique. So there's a 1 for that. That and that is another one. 2 of them there. And then finally, oh, come on, Thornley. There is another one. 6123. A. 38 is A. 39. So if you're going to do an addition or a subtraction on 2 numbers, then you have to add the uncertainties, which gives me 0.1. The IB prefers to have 1 sig fig here. Let's see if they stick with that in the question. So 0.10 is the only option. Okay. So it has to be B or D. And the percentage uncertainty, okay, so I suppose I better work out what's going on. The difference is 20 between these two. So it's 20.00 plus or minus 0.1. So to work out the percentage uncertainty, it's 0.1 over 20 times 100. Oh, that's just a half a percent. So the answer is going to be B. And the final question, 40. Oof, which technique can be used to find the bond lengths and bond angles? So X-ray crystallography, that's where you can find out how far apart the atoms are in the crystal lattice. by shining X-rays on. Bond lengths and bond angles. So maybe that's true. If I know how far apart they are and their distribution, maybe I could work out the lengths and angles. So A, maybe. B, H1 NMR. Now that's just to find the position of the hydrogens, not to do with the bond lengths and the bond angles. So that's wrong. C, infrared. Well, that's to do with the type of bonds. You can measure the bond lengths from it. The bond angles? Oof. I don't think so. No. I don't think you can measure the bond angles. You can measure the bond lengths, though, the type of bonds. And mass spectroscopy, no, that's where you get a molecule and you cut it with the little molecular scissors and into pieces. That's wrong. So I think A is the best answer. Is that right? 40A. My God, we're done. This is what I'm doing with my Corona lock-in time instead of playing silly video games.